First, let's answer any questions you have. So one of the questions came up with the old quiz I posted on Piazza. And so, what was the formula for that?
It was mg.
Mg.
And then bracket fe.
Fe.
And then parentheses cn.
Cn.
And then nh3, and there's 3 of them.
Okay. NH3, 3.
And there's 3 of those. And then en.
En.
Okay, and then
Close bracket and no charge.
Okay. And no charge on this.
Yes. Name and the coordination.
It's gotta be over CX, right? Okay, so we got try and
Well. Unfortunately, it's got to be a typo.
there's gotta be a charge, right?
Right.
Charging.
This has got to be a typo. And so, right, I mean, if we put a 4 here, then the coordination number goes 4 plus 3 is 7 plus 2, 9. Coordination number of 9, that's not going to happen, right? And so, unfortunately, this was a typo.
What was it
But,
supposed to
you know,
be? What do you think it was supposed to be?
it was supposed to be, this with, not 4, this can't be 4. This was going to be 3, what was it?
Yeah, it'd be 3 without the ethylene.
Yeah, the 3 here
And then
without the ethylene diamine, so that gives us a coordination number
But you'd
6.
have a plus 2 charge on the magnesium, no?
Yeah, but we have a plus 2 charge, and this would only give it a plus, or if this were
3
plus
and plus
2, and this was minus 3,
You could have a plus 1 on magnesium.
yeah, and then that would make it like this. So something that would be more sensible would be something like that,
There you go.
and then that would have worked. And so it was supposed to be that, I think. I just didn't completely change.
I had a question on another number.
Okay.
Nickel, then carbon 5 carbons,
Yeah, nickel,
and
like the carbonyl.
carbonyl. Can nickel have a 0 charge?
Can nickel have a 0 charge? Actually, nickel can have a 0 charge.
Wow.
Yeah, in complexes like this. Yeah. You look this compound up on Google or something. Did anybody look it up on Google? Hmm? Yeah, and so we would name this carbonyl. Not nickelate, because that only goes to nickel, just nickel. And I don't know, Roman numeral 0, what do they use for Roman numeral 0? Well, we're just going to put a 0 in parentheses. Indicate the charge on nickel is actually 0. So look, a lot of people don't add that 0 at the end, but you know, according to our rules, we should have it. People just usually call this pentacarbonyl nickel. Did somebody find some interesting property of pentacarbonyl nickel? Or interesting use? Why don't you take a look at it and see? There is. And so that was an odd one.
Zero. That's weird.
It's weird, yeah. It's weird. Uh-huh.
Is nickel the only one, or can
Others can do it too.
Cryotractic gas?
Are you sure that it's 5?
I read it.
Carbonyl with carbonyl? Because the coordination number doesn't.
Yeah, the coordination number comes out to 5, right? 5.
That's 4 or 6.
Typically it's 4 or 6, but
Unstable mode.
but you know,
Yeah, there's an iron.
yeah, there's iron, right? Iron and nickel. There's, yeah, nickel tetracarbonyl as well. But you know, if you look at this one, the waters are actually aqua ligands on the copper too. And in this one, is it 5 coordinate or is it 6 coordinate? You know, some people are thinking it's 5 coordinate copper 2 with 5 aqua ligands. versus a 6 coordinate with 5 aqua ligands and 1 sulfato ligand. This is an interesting story too, so look this up on the internet as well. And there's been some debate about the structure of this and how they resolved it, or what they think it is. What they think it is based on the vibrations that the complex exhibits. It's called infrared spectroscopy. You can tell the difference between, like, they're doing this thermal imaging of the Porter Ranch, gas leak. Methane is a good absorber of infrared. All right, it has a lot of different vibrations that it can have, and so this should be, even though methane's invisible, it's not invisible to infrared. Right, infrared can see methane quite easily. And so you can detect and see. But I guess I was listening to the radio and they said they aren't going to release those to the public. The public might be shocked to see images like that. Did they?
Thermal images.
Thermal images.
Billowing out of the.
Yeah, just billowing out. Yeah. But they have all. You can buy a thermal imaging camera for your iPhone or something like that, Android, and go take a look. Although, I don't know if that's, that might be infrared emitters. We're looking at infrared absorbers. Right. And so there are some weird species, weird species out there that we don't talk much about as far as bonding, like nickel, being in 0. And so that's always like a curveball, that somebody could throw out.
Not only that, it's got a coordination number 5 on that one.
Yeah.
So it's double weird.
Right. That's weird. Although, you've seen coordination numbers of 5 before in trigonal bipyramidal structures. All right. Other questions?
That's a nomenclature for the copper sulfate.
You would call it copper 2 sulfate pentahydrate. Yeah. But the actual structure people were thinking is like this, with 5 aquas, and maybe it's a trigonal bipyramidal type arrangement of aqua ligands, or they're thinking it might be like this, with a sulfato ligand and then 5 aqua ligands.
Wow, I don't know which one it really is.
Well, what can easily determine this is, and I don't know why they didn't do this. If you get a X-ray crystal. Do you guys remember X-ray crystal diffraction from the? That's one way you can determine crystal structures, where the atoms are positioned, by using X-rays.
Wow.
Using X-rays is essentially a picture of the atoms.
Was that the first accurate way we got to the crystallography of the structures?
By X-ray crystal diffraction.
Or the other methods that we used before that one? This would be the first, most accurate way. There are actually 2 types of X-ray diffraction. There's X-ray diffraction. The first type came much earlier. And you do it on a powder, with what you call a polycrystalline material. Polycrystalline. Let's see what your crystals look like. Is it more, a fine, tiny crystals? That's polycrystalline. If you do polycrystalline, what you can get is the unit cell. And from the unit cell, you might be able to figure out the atom positions. Versus a single crystal. For single crystal X-ray diffraction, you need big crystals. Big crystals, I'm talking about bigger than 1 millimeter or 2 millimeters. Actually maybe 1 millimeter in size. But it's sometimes very hard to grow 1 millimeter crystals. I was trying for maybe a year or 2 years trying to grow a crystal big enough. Yeah. And so I started reading about crystals and how to grow them, but it didn't work. And then finally I was able to grow a decent crystal by doing a series of recrystallization steps. This is what I said to some of those people who might have heated their beaker for a little too long and had some solids come out. Well, it's probably best to dissolve those and then try to do what's called a recrystallization. You know, each successive recrystallization, so you crystallize it and then redissolve it, crystallize it, redissolve it, each time discarding the liquid phase, you get purer and purer crystals. Yeah. And so that's what I was doing, a whole bunch of series, and finally I got it to grow. But, you know, I got this Russian book that was translated in English about the art of crystal growth from some professor at Moscow at the time. So I was just trying all different kinds of things. Yeah.
I added too much water to the mixture and it didn't solidify after ethanol.
Yeah, well, too much water is easy to fix. You know how to fix too much water? Just heat it. Don't boil it. Just heat it gently, you know, evaporate it. That's easy to fix, you know. It's a hassle, but it's not too difficult.
If we added ethanol already after we after it solidified, and then we might add a little more water.
Just be patient. This door will go.
If you added more water after the ethanol, and the purpose of doing adding the water step is to do what?
Is to dilute the ethanol so that it would let the water.
Yeah. If you add more water, then you'll probably dissolve some more crystals. Right? If you want to do recrystallization step, with ethanol in there are a couple of ways you could do that. You know, one, you add the ethanol and you get crystals coming out. And so, two, you just add water to try to redissolve those crystals and then add more ethanol. But the problem with doing that is the solution volume is increasing over time. And so probably one of the better ways is maybe to try to do a little bit of evaporation and then recrystallization. But the thing is, another thing that helps crystal growth is time. You know, slow growth with time. And so, you know, there's a trade-off because if you look at your crystals today and you go, maybe I would try a recrystallization, then you don't have much time because we got a filter today as well. And so you'll take a look at your crystals and see how they came out.
So if you get new ones, they're probably going to be small based on time. That's what you're saying?
Yes, right. Based on time, they're probably going to be small. All right. Other questions on chapter 24?
John, what happened?
Let's see. What are we doing today? We are doing filtration, and then we're going to have the quiz. The quiz is pretty short, right?
Hopefully.
How long did that? How long did that one that was supposed to take?
10 minutes.
Like 10 minutes. Yeah. 15 minutes.
And the name of that one where they added CH3 to that.
So we'll just have the last 30 minutes for the quiz or something like that. You know.
Was you getting our experience from last week's class?
Oh yeah. Yeah, I have your test, the reactions test from last week. And then I need to talk about some stuff. Since we're talking about the lab, let me just continue talking about the lab right now. And so we're going to finish the lab today. We finished the lab today. Then we have to start working on the report for the lab. Yeah. It's going to be a formal scientific paper.
Should that be done individually or with the group that we were in?
You're going to write these with your group, you know. And your groups can, actually you can adjust your groups if you need to.
Like if we had a failure, if we need some actual data?
That, or if it just is easier to meet with, you know, alternate group of people. It's flexible. Or you could do it by yourself, you know. That's always fun too. But how many of you have, let's see, have written the formal scientific report?
I think we might have done one. At the very end of Chem.
Okay, all right, that's good.
When we went to the computer and did that, you had to do draft like that and all that stuff. I think that's kind of
What are the components of a formal scientific report? This is going to be due quick. Yeah. This one you're going to have about 2 weeks, I think. I was thinking 2 weeks. 2 weeks for the lab report. Okay. In 2 weeks.
That doesn't mean a week or a week and a half.
Doesn't mean that we're gonna procrastinate.
Get it knocked out. Depends on me.
All right, so let me show you what are the components of a formal scientific report? Somebody tell me. Abstract. You know, abstract always comes first, and somebody tell me what an abstract is.
It's just a summary of what you want to be doing.
Yeah, basically it's what you accomplished in this lab. You know, what you did, what you accomplished. It has to be 1 paragraph in length, not 2 paragraphs, just 1 paragraph. There are word limits for abstracts. You know, you cannot exceed this number of words, but I'm not going to have a word limit on the abstract. You can exceed it. This is old paper here, quite an old paper, but usually people will have a title. And so let me show you a title. Here, this person forgot their title. Well, actually, I guess that is their title. What's the title? Synthesis Lab. That's okay, but you could be a little bit more specific and hit some key words in there. Right. And so this is a little more. I'll try to hide. It's a little bit better, but this is different than your synthesis. We synthesized a chromium, right, complex. This particular semester we did a cobalt complex. The cobalt's nicely colored as well. Cobalt's really pretty. Well, let's look at the chemistry of the cobalt, you know, because this paper should be describing the chemistry. So in the abstract, we're going to have a 1 paragraph synopsis of the whole thing, including, you know, the key results of the experiment. And so let's take a look at this abstract from the student. The purpose of this experiment was to synthesize, would be sodium, hexanitrito, and cobalt, Tate, 3. Yeah. From 2.5 grams of, what's that? Is that hexa, aqua, cobalt?
That would be 3, 9,
Is that cobalt 3 or cobalt 2? It's cobalt 2. And so we're synthesizing from hexa, aqua, cobalt 2, dinitrate or just nitrate?
Dinitrate.
Not dinitrate. Why not? It's outside the coordination sphere. Only stuff in the coordination sphere you do that. If it's outside the coordination sphere, there's no di. But this is cobalt 2. We need cobalt 3, right? And so what do you think? How do we get from cobalt 2 to cobalt 3? We got to do what kind of reaction, you think?
Oxidizing.
Yeah. Right, good. And so we have this plus 8 grams of sodium nitrite. First, the cobalt compound and the sodium nitrite were both dissolved in 8.0 milliliters of water. Then the solution was cooled to below 20 degrees Celsius. 5 milliliters of 50% acetic acid solution was added to the solution inside of a fume hood and allowed to react. And so 50% acetic acid was added. Afterwards, air was bubbled through the mixture for 30 minutes where the oxygen in the air reacted to oxidize cobalt 2 to cobalt 3. Then the solution was cooled, and with continuous stirring, 15 milliliters of ethyl alcohol was added. The ethyl alcohol precipitated out the ionic compound sodium hexanitrito-cobalt, Tate 3. The solution was covered in parafilm and sat for 2 days. Then the crystals were filtered using ethyl alcohol to wash out the crystals and obtain as much as possible, 0.19 grams of sodium hexanitrito-cobalt Tate-3 were obtained for a 5.84% yield.
Is that an A+
No,
abstract?
no yield.
It's a very low yield, but you know, we don't care about high yields. We care about high purity. And so, you know, the yield is not that big of a deal. For the sulfate lab, you cared about a high yield. You wanted 100% yield for that sulfate lab in Chem 1A. For this one, it's okay. But, you know, this is still low yield. But you're not going to be deducted for low yield. You know, I don't really care what your yield is. I'm not paying for the chemicals, but if I were paying for the chemicals, maybe I wouldn't care. Yeah. Well, I guess I am paying. I guess we're all paying for the chemicals. Your tax dollars. You might have a taxpayer advocate over here watching you guys, so you're not wasting any chemicals. Yeah, this is a good abstract. You know, does it give you a pretty clear idea of what they did and what they got?
Yeah.
That's all you need for the abstract. Just make sure. I like the abstract. What comes after the abstract? Not the purpose. We call it the introduction section. And so you could either have a little, you know, label, or automatically people are going to look at the next paragraph. The next paragraph's got to be intro. Most people, they'll block the abstract. That is, they'll cut in the margins and then change the font a little bit, or the font size a little bit.
So it looks different.
And so it looks different from the rest of the paper. The abstract is very important because most people, they'll stop there. They'll stop there because they already know what happened, right? They don't have to read the rest of the paper. The only people that will read the rest of the paper are the people who are very interested in what you did and want to know all the details. But, you know, most people have too much stuff to read, and so they aren't going to read the entire paper, and they'll just read the abstract. And therefore, when you go to you know, the library, they have books of just abstracts. And so you start reading the abstracts, and then you check off some abstracts that you're really interested in, and those are the ones you're going to read the entire paper. Well, the introduction, this introduction is very short. Do you see that? Only one paragraph. Maybe a bit too short, but what should the introduction have in there? Introduction typically has, let's say, a historical perspective, you know, what's been done in the past with this. Or has some insight, you know, highlights some synthesis or synthetic method or instrument or some type of analysis. Or it highlights, you know, the compound you're trying to synthesize or the reactant you're synthesizing it from. You know, what, it's a big deal. And so let's take a look at this synthesis here. I mean, not synthesis, introduction here. The introduction, they put a space here, and then we know the introduction starting here. Synthesis reactions are often used commercially by chemists to obtain a certain product or intermediate product. The series of reactions in this experiment was intended to synthesize this complex, but this product is special in that the type of molecules created is known as a coordination compound. Coordination compounds, okay, so this person's starting to introduce coordination compounds, you know, complexes there. And that's important too. You could talk about Lewis acids, bases, whatever, you know, stuff from the textbook you can include here. And that's what they did. Coordination compounds or complexes consist of metal center bonded to a species called ligand. Ligands act as Lewis bases when reacting with the metal and donate electrons to the central metal. The coordination number of a complex indicates how many points ligands are capable of bonding to the central metal. Some ligands are capable of donating electron pairs from multiple atoms on the same molecule. These ligands are called polydentate because they bite the central metal at more than one point.
It's very scientific until bite.
Well, you know, dentate comes from bite, so that's why I think they used it. But yeah, it's nice to keep it on scientific jargon.
Bond.
Yeah, bond. That's good. Coordination complexes were first proposed by the Swiss chemist Alfred Werner. So a little historical perspective on this. But the historical doesn't have to be on coordination complexes. The historical could be on this. You know, when was this first made? You know, who did that? You know, that type of stuff.
Alfred Werner, who said that certain metal atoms had two types of valence electrons, primary valence, for when the metal atom became an ion, and secondary valence, which determined how the atom bonded with ligands. Much of Werner's work centered on the study of isomers, and it was he who proposed that metals with coordination numbers of 6 would have octahedral structure, and prepared many optical isomers, including the first optical isomer lacking carbon called hexol. We don't have to talk about optical isomers, but you know, we need a reference for this. That's something that's missing. You know, where was this? Stated. It wasn't in our book, was it? No. And so that's one thing lacking here that's apparent. Also, you know, you're welcome to quote certain sections or large sections of whatever you want, but just make sure you know, give credit for that. Because if I start reading this and this sounds like Wikipedia, then I'm going to check it, you know, and see, well, did you just copy and paste it from Wikipedia? Because it just sounds exactly like Wikipedia. You know, you could do that, but you got to make sure, you know, you block it or whatever and reference. Otherwise, it's plagiarism. You know, or just write it in your own words. It's good.
I prefer to do that.
Yeah. Isomers are two different. So now they're talking about isomers. Isomers, are they really significant in this lab? Not really, but it's okay. So they went on talking about isomers and this and enantiomers. We haven't talked about isomers yet. Isomers are going to be covered in chapter 24, part 2. Okay, so they just jumped ahead.
Really advanced.
Well, I don't know, really advanced. They just started doing some internet research and found this, or looked in our book. You know, on this. This is, you know, this minor errors and stuff. It's okay. The compound sodium hexanide, this compound was precipitated out of solution using ethanol. Because sodium, the complex is ionic, it was not able to dissolve in the is ethanol nonpolar?
Polar.
Ethanol is very polar. It's miscible in water. But ethanol is a strange molecule because one end of it's highly polar, the OH end. The other end is nonpolar. You know, the ethyl part, the CH3CH2 part is nonpolar. So, you know, it's kind of a bridge or intermediate. And it was precipitated as yellow-orange crystals. Colors, we want to know about the colors, and we want to know about how it reacts. All right, that's on the longer side. Maybe let's look at an intro that's on the short side here. And so all this person wrote was, chemical synthesis is defined as the production of a substance from simpler materials after a chemical reaction. The synthesis is produced by the reaction of the combination of the chemical elements groups by the degradation of a complex compound. That's a little bit confusing for me. Chemical synthesis involves the breaking of existing bonds to form new ones. The synthesis of a complex molecule may have several reactions that lead in sequence from the starting materials to the desired product. One of the goals of a chemical synthesis is to produce a high yield of a product in a short time. Take a look at this person's yield. Compared to that last person's, this person's yield, 92.2%. Pretty good yield.
So awesome.
Yeah, compared to 5.6%.
I'm on the lower side.
All right.
Wow. That's so awesome.
All right, what comes after the introduction section? You can see it here, the experimental section. The experimental section just is a description of what you actually did, how much you mixed, what happened kind of thing visually. And in the experimental section, somebody should be able to repeat the synthesis in exactly the same way and to get exactly the same observations as you by reading this and yeah, essentially following the steps. This is the recipe that you use, not the recipe in the book, the actual recipe that you use, you know, with the errors or whatever else in there, variations, I should say. And so let's take a look at these two experimental sections. You know, this one is obtained approximately, you know, an experimental section always has to be in past tense because it's what you did. You know, it should never be like in the future or the present. It's always got to be in the past. And so that's why they say obtained, because probably the instructions are obtained. And then approximately 2.5 grams. I don't want to hear approximately 2.5 grams. I want to know how much you weighed out. You know, and so this person, this is not good. They should say, because our balance is weighed to the nearest 100, right? It needs another decimal. From the stockroom, and were dissolved in 8.00 milliliters of deionized water. 8.02 grams of sodium nitrate was weighed into, and the solid sodium nitrite was stirred into the cobalt nitrate solution until dissolved. The solution was cooled below 20 degrees C, the cold water bath. In the hood, 5.00 milliliters of 50% glacial acetic acid. You know what glacial acetic acid is? It's like pure acetic acid. It's liquid. It's hard to get it 100% pure. There's always a little bit of water in there.
Like super vinegar?
Yeah, this is like, you know, vinegar is 5% acetic acid. This is close to 100% acetic acid. And so it's concentrated. You like vinegar? Yeah. Were added dropwise, prepared with 5.00 milliliters of 17 molar glacial acetic acid and 5.00 deionized water. Then the solution was transferred to the oxidation apparatus in Figure 1. So let's take a look at Figure 1's oxidation apparatus here. These were from the procedure for the cobalt synthesis, which isn't in our lab manual. It's a handout. So that was the figures, and they just I don't know what they did, scanned it or whatever. So we want to know things like color. Like for example, they didn't tell me what color this is. You know, that's a negative. You know, I want to know what color this stuff is. Not only that, I want to know, is it powder or were there big crystals? Is it pasty? You know, semi-solid, etc. All right, the solution was, it should be then oxidized in the oxidation apparatus for approximately 30 minutes. Afterwards, the solution was bubbled through the apparatus and trap the toxic NO2. Okay, that's not so clear what's going on here. You know, they should have rewritten that part. But we do generate some toxic gases in this. Then the solution was filtered with the funnel and cooled on ice. We added dropwise 15 milliliters of ethanol alcohol. No, it should be ethyl alcohol or ethanol alone, until yellow-orange crystals were formed. Crystals remained on ice for about 5 minutes. Subsequently, the solution of yellow-orange crystals was stored overnight in the locker. On 9/13, the solution was filtered using the vacuum pump apparatus, shown in Figure 2, I think. What they're saying, Figure 2 vacuum pump. They should have just written it here. The crystals were rinsed with 1 milliliter ethanol and washed with about 10 milliliters of ethanol. Crystals and filter paper were transferred, etc. Here's another experimental section. I won't read the whole thing, but you know, let's see. You know, first my partner and I measured out 2.5 grams. Again, the precision's wrong here, but all right. synthesis, we aren't so careful. So this is done in the fume hood. You know, the solution was then added to a test tube and had air bubble through it. The gas produced by the mixture was toxic NO2 gas. The toxic NO2 was fed to a flask filled with 1/3 water, where the NO2 dissolved and formed nitrite and nitrate ions. That's much more descriptive what's going on. We left the solution to be bubbled with air, etc. So you can see different degrees of detail. And people, you know, when you think about how much detail that you need, you know, sometimes the detail is excessive. Like, you know, I walked over to the balance, but there were some people ahead of me and I had to wait, and then, you know, you don't want that kind of detail. Or, you know, what size beaker. You don't really even need to say what size beaker, because any size big enough will work. You know, if there's a specific size, only a 100 milliliter beaker will work, then you gotta worry. You should specify that, but, you know, a lot of these details we don't have to include.
Excuse me?
Uh-huh.
Dr. Janao, one partner helped me doing like the wrong size beaker. Like, I put the oxalic acid in a 50 milliliter beaker instead of a 200.
That happens. I mean, that happens to everybody. You put in too small of a beaker, and then you have to escalate the size. It happens all the time. People start off with a small test tube, and then the solution starts to grow, and they're getting bigger and bigger test tubes, and finally you give up on test tubes and start using beakers. And at that point, you probably should do an evaporation step. Otherwise, you're getting way too much volume in your solution.
Or losing it too much.
I know.
All right. After the experimental is just kind of the nuts and bolts. This is the cookbook, right? But the experimental, we don't go into the chemistry. We don't go into, you know, what the actual reactions were, what the theory underlying this, or the calculation. Only simple, you know, factual data is in the experimental section. What we mix together. After the experimental section, I had them write the results and discussion. What's the difference between results and discussion? You know? Results is factual data. That's your results is typically raw data without analysis. Discussion is the analysis of your raw data. The reason why scientists separate that is, does somebody know the reason why scientists separate the raw data from the analysis of the raw data? Your analysis could be wrong. Right? And so sometimes you see, not sometimes, but, you know, periodically, actually, when I was doing a lot of literature searches, I found these papers all the time. You know, a paper would be titled Reanalysis of So-and-so's Data, because they completely disagreed with the analysis that was done, or new theory came up, or new computers, or new whatever came up, so that they could get a better interpretation of the raw data. The raw data, though, it's factual. Remember, theory always has to agree with experiment. And experiments are fact. All right, but what we're going to do is we're just going to mix it up here, you know. In other reports, we're going to keep it separate. And so this one we aren't going to worry about it. We're just going to mix everything. And so after drying the measured precipitate, then they calculated how many grams of precipitate they got. But the thing is, do you know this 0.19 grams is this pure? How do you know the precipitate is this, other than you're told it's that? You know, I know it's that precipitate because the book says it's that precipitate. Is that good enough? No. No, you have to justify it, or you have to convince somebody. You know, the thing about scientific papers, they have what are called refereed. Have you heard of refereed papers?
you know, or reviewed papers versus papers that are not refereed. And there's a big difference between the two. You know, on the internet you can publish anything because it's not a refereed source, right? But in a scientific journal you can't publish everything because you have to get it past 3 referees or more before they even consider publishing it. And the referees act like, you know, critics. They want to make sure they catch any errors or whatever else in there. And this is, you know, everybody acts as a referee. Like, for example, you know, it's part of your, it's like jury duty, you know. Everybody does it when you're working in particular fields. Well, anyway, let's go on here. I'm not so convinced that those, I need some more chemistry before I'll accept those orange crystals as this, right? You got to tell me what's happening here, you know, in some kind of discussion so that I believe you. And so that's what your purpose in this results in discussion is to go through this and at the end then say, you know, makes sense that we end up with pure, you know, sodium hexanitride and cobaltate 3 because we did all these steps, right? But, you know, if you say we ended up with this because the book says, then nobody's gonna listen to you. Basically. And so I typically wouldn't start off with something like this. You know, I'd start off with the chemistry here. You know, what's happening. They ended up with it, and so let's see if these guys started off. These guys started off more with the chemistry of what's happening. You look at their discussion. This should be results in discussion because there's no separate results section. It is possible that many side reactions happen. Well, if there's side reaction, maybe this side reaction's causing impurities into your product, and you want to know, are you getting any kind of interfering species, you know, or co-precipitates, or other common, you know, impurities that might occur in the synthesis. Well, anyway, let's see, but we can account for one key reaction in 3 sides. Well, I don't agree with this exactly the way it's stated, but the experiment started with dissolving 2.5 grams of the red orange. This is the cobalt-2 complex into water. Okay, so they're just showing it dissolve over here. And so it's an ionic compound, so it's going to break apart these species. Afterwards, we added 8.02 grams of white solid sodium nitrite to the previous solution until dissolved. At time of reaction, it turned dark red solution and then cooled from room temperature to about 20 degrees C. When added 5, you don't have to get into a lot of these details because the 8.02, wasn't that up there in the experimental? So you don't need to repeat the numbers here. You just tell me what happened. When you mix the solid sodium nitrite with that, this is what happened. If I want the numbers, I'll just look up higher, right? And so basically you explain in words, you know, the reactions, and then you show it in equation form. And so I need to see both, right? Words and equations for this type of stuff. Then you'll just go through and talk about the reactions. So the first one was or this one, I guess it continues here. What kind of reaction is that? Oh, I'm sorry, the redox reaction here. Redox. Where we can see that nitrate and H+, actually this is a side reaction here. The main redox reaction is here. This one does have a side reaction. The main oxidizer is O2. And so the O2 is going to oxidize the cobalt from 3+ to 2+. And here's the net reaction here. So you could talk about that. There's nitrate present. If there's nitrate present with acid, that's also a very powerful oxidizer. And so this is the side reaction that generates the toxic gas, because in this redox reaction, when nitrate reacts, it forms nitric oxide or nitrogen monoxide. Nitrogen monoxide is easily oxidized in air to nitrogen dioxide, which is brown. Nitric oxide is colorless, and so we go from a colorless to a brown gas here. And so that's this is the side reaction that produces the toxic gas, which is killed in. Let me see if they show the step in where they kill off the NO2 gas. Okay, what's this next reaction here? Is that redox? They got the charge messed up. That's probably a typo there. This, I don't know what that is. Doesn't look like anything to me. Uh-huh. Yes, Kelly.
Okay. Well, what if you don't understand what's happening chemically?
What's happening chemically?
Yeah. Because like when you explained the chemical reaction that happened the other day, it didn't make any sense to me.
Didn't make any sense to you? Well, that's why you have partners to help you with this. You know, you work with a partner in writing the lab if you want, and then maybe you put your both heads together, you can figure it out.
Okay.
Just like I did for you guys, I did this for these guys. You know, but it's always, you know, it's always kind of amazing when I write equations on the board, and then when I look at the reports, sometimes there's no match at all.
Uh-oh.
Yeah, I wonder, you know, that this is sometimes. And then, you know, I realize that some people just don't write notes. They don't like to write notes. And so I get some bizarre equations that pop up. But it's not meant to be difficult, you know. They're missing one, though. You know, like this equation, I have no idea where this equation. This could be just miscopied notes or something like that. This equation, you know, this equation's the presence of ethanol is going to lead to this metathesis reaction. So it's missing. There's a missing reaction here. I know what reaction's missing. Do you? So anyway, they talk about the reactions, and they go down, and so it's starting to make sense. Yeah, we should be forming this, and they should talk about any side reactions or any other issues that might come up with these particular steps. But for your reactions, no major issues. For this one, there were. And then once they do that, then, you know, and you wash off the crystals, then, you know, you can have a reasonable degree of confidence that this could be what you synthesized, right? But a reasonable degree of confidence isn't usually enough. You know, scientists, they want more than, you know, this is what we think we got because we did all these steps, right? And so usually when you have a synthesis paper, there's two parts. Do you see it says synthesis? If you look at the literature, most of the papers out there are going to say synthesis and characterization of such and such. What does characterization mean?
It's analysis of the crystal, like whether it was pure, the purity of it.
Right, you would be analyzing your final product, you know. You would analyze it. What ways can you analyze? Well, you could measure some of its properties, which might tell you the purity and composition, structure. So what types of properties are often measured in characterization? Yes?
Melting point.
Melting point.
Color.
let me stop at melting point for really quickly. If you continue on in organic chemistry, melting point is used all the time to identify, products, because, most products will have a slightly different melting point. Sometimes, by coincidence, the melting points match, but most of the time they're different. But, melting point can tell you, the potential identity. You might not want to use melting point alone. You might want to back it up with other characterization techniques. But the other thing melting point tells you is this. When you melt a crystal, all the bonds should be the same because the crystal's well ordered, right? And so, what happens is, all of a sudden you hit that temperature and it turns into a liquid. It just liquefies at that temperature. And so you heat it, you got this crystal, and all of a sudden the crystal plops down, it's liquid, right? But if you have a lot of impurities in there, what the impurities do is they start screwing up the bonds. And so when they start screwing up the bonds, some bonds are weak, some bonds retain their strength. And so what you get when you have impurities is you get something called a melting point range. It doesn't just melt at one temperature, it melts over a range of temperatures. So as you heat it up, the weaker bonds start to break, and that starts to melt. And then the medium strength bonds, and then the stronger bonds. And so the wider the melting point range, the lower the purity. The tighter the melting point range, the higher the purity. And so we use melting point, and you can buy these commercially available melting point apparatus where, it's a little microscope, a little heater, and a thermometer. And you just watch the thermometer and look through the microscope to see when the crystals melt. And they have those next door here. And so melting point's a powerful technique, but a lot of these ionic compounds melt at extremely high temperatures. And so I'm not sure how practical that is for us. Because if you have something that's melting at 700 degrees C, are you going to be able to use a little heater to do that? No.
No.
You're going to need a flame or something to melt that.
Like propane flame.
Yeah, something like that. Or more. Do you know of any other characterization techniques? Another characterization techniques is what we just talked about earlier, X-ray diffraction. X-ray diffraction, especially powder, is very quick and easy. You can run a powder X-ray in a minute. If you do a single crystal, it's going to take you a long time, etc. And so you could look those up on the internet, but that's something that's missing here. You might see something else that's missing. Something else that's missing is a conclusion. Do you see any conclusion section here? No, in general there's not. For a short paper you don't write a conclusion, This paper just ends like this. This paper ends with their calculation for percent yield here. And so they talk about the calculation and then they show the equations for the calculation. But, a proper conclusion, would be things like, not like error analysis. Error analysis just belongs in the discussion. And so you don't say, I made a mistake here, I might have lost something there, we might be off. A lot of people say, I got 92.2% yield, that means I lost, 7.8%. And then they say, due to experimental error, but that doesn't really tell us much. And so normally what people do in a conclusion section is they talk about, what they would do in the future or what they would recommend someone to do, or what they would do if they had plenty of money, to buy whatever they wanted to buy. That's what people talk about in the conclusion. Where should this go next? Not a summary of what you just did. Nobody needs a summary of what you just did in a short paper. The abstract is that, yeah. So you don't need to repeat the abstract and call a mini abstract at the end. You want something new. Conclusion should always contain something new.
So for this one, would you recommend we have a conclusion? You're not necessarily.
No, you could have a conclusion, but you got to be careful what you include in the conclusion. If you wouldn't call it a conclusion section. You just have an ending paragraph that says, what? Well, don't overboil. You could just have that in the regular discussion. In conclusion, I overboiled it. No, not really, because you just want to read that in conclusion. I think that we got to this point, but the next, step should be this. Or, you know, in the conclusion, I think this whole procedure should be scrapped and then redone my way, you know, which is much better, let's say. There's something like that, you know. It's your opinion about that kind of stuff. But okay, now that we've done this, you know, would you say something like this? In conclusion, I say my orange crystals are 100% pure. See, you know, because you got to trust me. Trust me. Yeah, I nailed the experiment. They've got to be 100% pure. Maybe, right? But you know, I wouldn't feel comfortable. Well, so do you have an idea? And then you'd have some kind of reference section. Yeah. 2 weeks. Yeah, you know, writing the whole thing from start to finish, just give yourself like a little time limit. Say, you know, I'm going to try to complete my rough draft in an hour or hour and a half or 2 hours at the most. And then just write the rough draft. And then swing the rough draft by me. I'll take a look at it and then give you some comments. Okay?
But is it okay if we get negative feedback?
You want negative feedback.
I know what you did wrong to fix it.
Yeah, you know, unfortunately, science is full of negative feedback. But you get used to it, and actually you welcome negative feedback. You like to hear negative feedback after a while. You know, too much positive feedback is, you go, Yeah, I want the negative feedback. You know, just go ahead and blast into it and tell me, you know,
What can I do better?
why you think my paper sucks.
Yeah.
That's, you know, you don't want these nice comments and then some little glancing below saying, oh, this paper was really a piece of garbage.
From nice
But,
feedback, you learn from the negative feedback. How you can do
But,
it.
you know, there's good, yeah, I'll try to give you positive feedback. I'll try my best to give you some positive feedback. Like these papers, you know, I wasn't totally negative on these papers, even though they were mistakes, right? Little mistakes I'm going to
My
overlook.
brother's pretty harsh critic. My brother's.
Your brother's a harsh... Then have your brother review your paper before you turn it in.
That's right.
That's the best. Or, you know, at the very least, I don't know what the line is, but over in the English Writing Center, you can bring... some people did that. They were uncomfortable with the grammar, so they brought it in, and they really fixed it up, even though they didn't know anything about the science, but they made it clear.
It's out that door and in the next.
Oh, really? Yeah, then you should go there, you know, if you want. They're probably going to help you a lot with the paper. But try to whip up a rough draft to show to me next week. How about that? Okay? All right, great. All right, let's take a break and then start the lab. Hopefully you guys got some nice crystals you can show.